For this video, we will discuss equations of state. Okay. In reality, diba, ano ba nangyayari? Real gases do not behave ideally, and the reasons why is because, number one, the molecular collisions are inelastic. Okay? So they are inelastic, and if the density is high in actual gases, meron talagang intermolecular forces of attraction. Kasi diba, sa ideal gas, we assume it to be negligible. But in reality, there exists the intermolecular forces of attraction. And the first equation of state, alam nyo na to, is the van der Waals. So, hindi ko na masyado i-emphasize to. But this is the equation. Oops. This is the equation. Okay, and then we have the formulas for A and B. Okay. So, in the formula, merong P critical, P critical. Okay, P critical, P critical na mahanap sa literature. And when these constants, A and B, are taken to be 0, ano mangyayari do sa van der Waals equation if 0 yung A and B? So, we are left with P equal to RT over V. Okay? And that is just the ideal gas equation. So, si van der Waals, sa kanya pinangalan yung equation, he wanted to improve yung ideal gas equation of state. So, by considering the two factors involved in real gas behavior. So, yung isa is yung intermolecular forces of attraction. So, dito sa term na yan, dyan ako consider yung intermolecular forces of attraction. So, the other factor is the volume occupied by the molecules. Kasi sa ideal gas equation, inassume na negligible yung volume occupied ng molecules. Pero sa totoo lang, di ba, meron naman talaga siyang volume. So, dito sa B, okay, sa constant na yan na consider yung volume occupied by the molecules. Again, yung dalawa, yung A and B, makakalculate natin sila by using this equation. Okay, so specific sa type, sa kung ano mang klaseng gas, ay yung values ng critical temperature and pressure. So, it depends sa type of gas. Okay, so, isa pang basis ng van der Waals equation of state, we can check the PV diagram. And dito sa PV diagram, let's locate the critical point. Okay, so ito yung critical point, diba? Siya yung nandun sa pinaka-top ng curve. So, this is the liquid region, this is the vapor region, this is the liquid vapor region. Okay, this is the PV diagram, diba? Now, we have isotherms. Okay, itong mga lines na to, this is one isotherm. So, this isotherm na to, obviously, yung temperature niya is yung nasa itong topmost isotherm, yung temperature niya is greater than the critical temperature. Okay? Kasi yung critical temperature, ito yun, yung nag-touch dun sa critical point. Okay? So, ano mapapansin natin? Merong horizontal inflection dito sa critical point. Itong isotherm na to. Thus, if we take the first and second derivatives of P with respect to V, okay, at the critical point, it must be 0. Saan ba natin natunan yun, di ba? Sa math, sa calculus, di ba? If inflection point, yung first and second derivatives niya, doon sa point na yun ay 0. Okay? So, ito yung first derivative ng P with respect to V. Ito yung second derivative. Pareho siyang 0 at that critical point. Ayan. So, by differentiation of the van der Waals equation and by eliminating V sub C, okay, na-determine ni van der Waals yung constants na A and B. Yan. So, yun ang method ni van der Waals para ma-derive yung constants A and B. Ayan. The second equation of state would be the Beatty-Bridgement equation of state. So, proposed ito noong 1928, whereas yung kay van der Waals earlier, balikan natin. Kailan nga ba ito na-propose? 1800s, no? 1873. So, itong Beatty-Bridgement, na-propose siya 1900s na. So, 1928. And anong feature nitong Beatty-Bridgement? Based on 5 experimentally determined constants. So, take note, experimentally determined constants. And it's reasonably accurate for densities up to 0.8 of the critical density. Okay? 0.8 of the critical density. So, yung critical density is the density of the substance at critical point. So, yung pwede mo siyang i-apply if yung critical density ay less than yung density nung substance mo ay less than 0.8 nung critical density. And this is the equation of Beatty-Bridgement. Mas mahaba siya. Pahaba yan. Pahaba eh. Okay. Mas mahaba siya as compared to van der Waals. And then, ito rin yung mga equations ng capital A and capital B na constants. Okay. We also have the Benedict-Webb-Rubin equation of state. So, extension lang siya nung Beatty-Bridgement. 1940s naman siya. Okay. Na-develop. So, if the Beatty-Bridgement may 5 constants, si Benedict-Webb-Rubin ay may 8 constants. So, mas mahaba pa yung equation as compared to sa Beatty-Bridgement. Ayun. And mas accurate na siya, hindi lang siya 0.8 ng critical density up to 2.5 ng critical density. Accurate siya. And then, in 1962, after 22 years, okay, si Strawbridge, nag-develop pa siya ng isa pang equation of state. So, from 8 do sa Benedict-Rubin, okay, si Strawbridge, naka-develop siya ng up to 16 na constant. So, hindi napapakita dito yon, pero obviously, mas mahaba na yung equation niya. And ano yung advantage ng mga equation of state na bago? Okay, ano yung advantage nila? Mas accurate sila compared kay van der Waals or compared dun sa nauna na equation of state. Yung applicability niya, mas lumalawak kasi nung una, 'di ba, 0.8 nung critical density, pero ngayon up to 2.5. So, yun, mas maganda yung equation niya, kaso mas mahaba. siguro nagtatanong kayo, ano yung lalagay nating mga constants, ano yung value ng mga constants na i-input natin doon sa equation. So, yun, makikita natin sa literature, okay, sa references. For example, for Abridgement, ito yung mga constants ng mga common gases. So, we have air, argon, carbon dioxide, etc. Ito yung mga A naught, small letter A, B naught, small letter B, C. Yun yung constants nila na i-input sa equation. Again, makukuha to sa literature values. And the fourth equation of state would be the Virial Equation. Okay, so paano naman na-derive yung Virial Equation? Balik tayo sa PV diagram. Anong observation naman? Ang observation dito sa PV diagram ay yung isotherms ng gases and vapor. So, saan ba yung region na yun? Diba, ito yun, yung vapor region. Okay. To the right of the saturated vapor line. Saan ba yung saturated vapor line? Ito yun. This is the saturated vapor line. Okay. When we say saturated vapor, ano nga bang ibig sabihin nun? It's not about, diba ang wet vapor, okay, pag nasa loob ka ng saturated curve, combination ka ng saturated liquid and saturated vapor. Pero, pag nandito ka sa curve itself, on the curve itself, 100% saturated vapor ka lang. Okay. So, balik tayo kay Virial Equation. So, doon sa observation natin, yung mga isotherms dito sa region na to, ano mapapansin nyo? These are just simple curves wherein nagdi-decrease si V as nag-i-increase si P. So, as we increase the P, yan, diba? As we go from lower to higher P, so pag ganun yung direction nung sa P, ano nangyayari kay V? Pag ganun yung direction ni V, so nagdi-decrease siya. And then, for a given temperature, the product P times V should be more nearly constant and can easily be represented as a function of P. Okay? So, we can express the PV, okay, yung product na P times V, we can express it for an isotherm. Okay, so meaning, pag sinabi natin isotherm, di ba, it's just one temperature. Okay, as a power series. Yan, as a power series. So, ano ba nangyari dito? Una, yung V, niligay lang, dinivide lang yung right side ng equation ng V. Okay. Then, in-express yung P, PV equal to RT, diba? In-express lang siya as, yung P in-express as T over V times a constant. Yan, itong form na to na transform into this form. Ano na siya, hindi na siya in terms of pressure, but in terms of temperature na siya. Okay, so, wherein, okay, itong mga A sub T, A of T, P of T, etc. are called the virial coefficients, and these are functions of temperature alone. Okay, so, these are functions of temperature alone. Okay, so the PVT behavior of a substance can accurately be represented by the Virial equation over a wider range. Okay, if we include a sufficient number of terms. So, di ba pag sa power equation kasi pwedeng putulin. Okay, pwedeng putulin yung, bawa, ito lang i-consider ko. Pero, as we increase the number of terms in the equation, ano nangyayari? Mas nagiging accurate yung estimate ng pressure. Okay, so, as you include more terms, mas nagiging accurate. Ayan. Pero, if ang condition lang naman natin ay low pressure lang tayo, sufficient na yung dalawang terms. It provides satisfactory results na. So, more or less accurate na if we just use two terms. Ayan. Okay, so that is for virial equation. Let's move on to Redlich-Kwong equation of state. 1949, so mas later na siya than the Van der Waals. Pero hindi siya kasama ng mga Beate Abridgement. Hindi siya kasama ng mga Benedict Weber-Rubin. So, ibang branch siya. Iba din yung naka-discover or naka-develop pala sa kanya. So, obviously, more accurate siya sa Van der Waals. And ito yung itsura niya. So, kahawig pa rin, medyo kamukha ni Van der Waals yung equation. Yung dalawa yung terms, tapos, merong A at B na constants. Kahawig siya, pero mas accurate siya. And ito yung formula nung constants niya na A and B. So, gumagamit rin ng critical temperature and pressure. Okay. So, stop muna tayo. Next video na tong example.